Hi, back again. Sorry to stop the first part because I found this too long, so I separated it in two lectures. We've talked about the setout versus measurement. What I want to show you, what you can see in most of the textbooks is on the left hand side, but what actually is happening is the picture on the right hand side. That if we assume that we are measuring the distance roughly 250 meters, and then the errors in the zenith angle is plus or minus 5 seconds, error in distance is plus or minus 5 mil, and if we have both of them at the same time, you can see in different colors how it's affecting the zenith angle degrees, how it's going to affect the standard deviation of the height. As you can see, if you have the distance error, it's going to drop dramatically, or if you only have the angles, but if you have the balls, it's going to be the blue curve up there. But yeah, this one is quite, what you see in the text out there is not quite right in the setout, or it doesn't apply to the setout to me. So in next bit is mostly concentrated on the least square adjustment and weighting observation. I know you had the weighted observation in COMSB, so please go and review your book SVY2105 obviously. In the weighted observation, basically weights can be based on experience, condition, equipment, procedure, and so on. Usually they are assigned as the inverse of variance to the measurement, so it's like this obviously, and is mostly valuable for least square adjustment, where we have the weighted observation. So I really appreciate if you can go and review. If you are not sure, have a look at the example. I'll put the example in the study book. I've skipped that for here because we don't have enough time to go through all the examples. Hopefully you read both lecture notes and the study book, and you make sure that you understand all the terms. So least square analysis, again, in here we are not going through the math, like how you're going to calculate calc space of that. What I'm trying to do here, assuming that you know least square analysis from COMSB, which is complex, I know is a tough one, but basically least square analysis is particularly suited to complex multi-observation types when there's a considerable redundancy and we need to adjust it. Basically we have two types of adjustment, as you know, minimally constrained or fully constrained adjustment. Basically it's very important for you as a surveyor to have the least square adjustment knowledge and to be able to know whether you can meet the standard requirement. So having said that, we assume that you've covered all the least square extensively, I think COMSB. But here what we are looking at a priori and post priori aspects of the network constraints. So we're going to analyze the result, interpret the results, and find out what they mean and how we're going to meet the certain standard requirements. Let's have a look at the minimally this one is fully constrained network. Basically it's a constraint model. We're assuming that P1 and P2 are fixed. Yep. And then we have the traverse running from 102, 103, 104, and then so it's basically traverse is going from P1 to 102, and then from 102 to 103. So I'm going this way, then from 103 to P2, and then I'm coming back to 104, 102, and basically 103. So this is how it's run. So I'm removing that because I put too many lines obviously. I just want to show you how it's going to be, how it's actually working. So having said that, and assuming that we use the total station with this accuracy that I've mentioned here, like a distance accuracy and bearing accuracy of plus and minus 4 seconds, and distance is 2 millimeter plus 2 ppm plus or minus. So P1 and P2 are fixed, so it's a fully constrained, and the standard deviation of which is, we call it, what do we call it? Positional uncertainty, because it's relative to the national datum. Yep, it's plus and minus 12 millimeter. So this is as like, if we have this, and then key is that the adjustment has stretched the line beyond the expected precision. What does it mean? It means the precision of the PSMs is not significantly better than the traverse. I told you that if you measure, for example, 102 to 103, having said that, we have this accuracy here, 2 millimeter plus 2 millimeter. For example, say the accuracy we measure is going to be plus or minus 3.2 millimeter, but after adjustment you're going to have the accuracy of 5.8. Similar thing for 103 to 104. You can see the accuracy of the measured is better than the adjustment or adjusted distance. The reason is the survey uncertainty is better than positional uncertainty, because if I go back, the equipment we have is pretty good, yeah, and we can measure the basically survey points in very good accuracy, but initial position accuracy uncertainty for those points, or PU, is plus or minus 12 min. No matter how good is your survey uncertainty, your measured distance are going to be better than adjusted one. So, which is basically obvious from the error ellipse that you have here. So you can see that it's basically the adjustment has stretched the main traverse lines. So this one part of the analysis that you can see is the fully constrained, assuming P1 and P2 are fixed. But let's say if we have unconstrained adjustment and we just have P1 fixed. The picture on the left hand side, in the scenario we don't have any gross error, so everything is fine, looks fine. But if we introduce the gross error in one of the legs, say if I introduce the gross error in this line, I assume that I haven't measured the distance correctly, or I have inserted something wrong, like prism constant for that line. When I measured, I entered the wrong prism constant. But when you get the least square adjustment, you will see the result is going to be looks like that. So you can't really see basically the adjustment with the gross error basically doesn't show the large error ellipse only for that line, but it shows the large error ellipse for each of the lines. So it means that least square tries to distribute the error even if it's not for all of them, even if it's only for one observation. So the problem is then the detection of that error is going to be so difficult. So because it's not isolated, so it's going to be distributed among all of those. So let's have a look at another example. In this example, it was the gross error. Yep. How about if we have systematic error in all of our observations, not only one? As I said, rather than having one gross error for one observation, if I have systematic error, like prism constant, for all of my distances that I have measured, then the final results of adjustment would be the figure on the right hand side. So if I put those figures on each other or overlap them, you can see the scale nature of the error, which is in this case can be prism constant, is basically scale the network. So systematic error basically could go undetected if the traverse is unconstrained. So systematic error is just prism constant, wrong ppm in atmospheric, grid scaling correct. So this is how it's going to affect your network adjustment. So, but you might say, hang on, don't we have the statistical test for our least square adjustment? And if it passes, yeah, everything is fine. If it's wrong or it doesn't pass the test, I can say, no, it's not wrong. Sorry, it's not right, and it doesn't pass the test. Yes, it applies to sometimes, but you have to be careful about the statistical testing. They are basically, a statistical testing is a range. They are inferential. What inferential means is like they probably correct for certain situation, but it doesn't apply for everything. So you can't rely overall. You can't rely on the statistical testing solely and say, this is it. If it passes, all right. If it's not, it's not. No, you have to do further analysis and make sure that your field procedure, equipment, computational procedure, your assessment, everything is working fine and they can meet the standard and requirements. I give you the example. Just imagine we have the 300-meter distance that we want to measure it, or we've measured it 24 times. Assuming we use the instrument with 2 millimeter plus 2 ppm plus or minus obviously EDM accuracy, our sigma of or standard deviation for 300 meters obviously is 2.6 millimeter if you put that. But remember, if you want to do the sigma mean would be different because we've measured that 24th time. Yep. So this is how it works. But let's look at some of the case or scenarios. In case A, I would assume everything is fine. I've measured that distance, which is 312 meter in this example roughly, and I've come in with the standard deviation of total observation in 2.6, the standard deviation of observation 2.7. We passed the chi test, F test, T test, so all tests have passed. Observation or confirming the equipment specification. Yep. So I have this bit here. Sorry, I don't know, it's coming every time. This is the equipment and this is the observation that we have. So they're confirming each other, so it's meeting that. So on the right hand side you can see the plot I put is the is basically a plot of observation showing a linear fit. So you can see these are my observation. Yep. And then I plotted the regression line to show the linear fit, and this is the basically histogram of the residual. And you can see everything is fine. Everything looks to be within the limit. And there's no problem. Yeah, let's move on. But in case B, what I've introduced the basically blunder in one of my observation to don't match to another observation. You can see it's easily detectable from the diagram I had on this here, and this is obviously the residual, which is way out of the limit. So you can see I've introduced the blunder. The residual is 8.7, which is 3.6 times of the equipment standard deviation. So equipment standard deviation is, if I'm drawing the normal Gaussian, we know random errors are Gaussian normal. Equipment standard deviation, which is 68. So basically, in reality, all of your measurements should lie in this region. which is minus 2.6 to plus 2.6, which is mostly the case. Sorry, it's 95 confidence interval, so you times 2, so it's 2 sigma. But this is more than 2 sigma, it's more than 3 sigma. In reality, if you have any measurement or observation which lies more than 3 sigma, then we call them outlier or blunder, and you can remove them. So this is a statistical test, what they call it. But what I want to show you, if you look at the test, they all again passed. Removing this one. Sorry. Just give more space. So what I want to show you, no matter whether you have a blunder in your observation, still you meet somehow, you're close to total station specifications, instrument specification, all of your test has passed, so there's no problem. And if you're just looking at the test, you can't really detect that. Moving to case C. In case C, I've introduced the blunder in observation from observation 13, this bit here, to 24. Half of my observation has a blunder. They appear to have movement of the prism. So what I'm saying, you can see, it's like, yeah, it's okay until this bit, and then you have a big jump, and then the rest follow each other. So to me, that jump might be the prism has jumped, or it's going to be your something has changed that moved, or maybe you bumped the instrument. Something moved that caused that drift or jump in your observation. Again, you can see chi test is passed, but F test it didn't. So, but it says that always do all the tests. Don't rely on one test only. Try to do all the tests. There are some tests are different and sensitive to some factor, which is not the case for all the tests. So do all the tests. Make sure that you plot the observations. Visualization is very important, guys. If you plot your observation, you always detect your error. So make sure that you have a look of your observation. You make sure that you understand them, and make sure everything is alright. Last scenario, in case D, what happened here is basically the yellow line here again shows observation. You can see observation goes up. So there is a trend in the observation. So I can see my observation is increasing while I'm going. So it might be your prism tripod could go slowly subsiding on one leg and cause that error in your observation. So it's something happening over the time, obviously. So it's definitely it's not right. Good? It's not right, but you can see if you're just looking at this bit here, everything is fine. Your standard deviation of observation is very close to the standard deviation of a specification. All the tests is passed. But is it really correct? Is it really accurate? The answer is no. So it's pretty much like case A, but that's not true for sure, because you have something going up and you can see that your distance is increasing over the time. So that's why it's very important for you to understand the errors, try to visualize them, try to see why these things happening. So the thing is, yes, statistical test is necessary for everything. There are good evaluation, analysis, and tests, but this shouldn't be solely assessing the quality of measurement. You have to do other testing process to have more insight about the errors and detect identifying the errors and how it looks like. So don't rely on the pass and fail test. Other thing is also carefully look at the test numbers. Some of the tests passing very closely to the boundary, like if the boundary is 1.5, I don't know, 27 or 29, sorry, it's passing by 2 mil, so it's very close to failing. So you should realize that something's going wrong. Although that this test is passing, is very close to fail. So you have to identify whether there is any blunder or systematic error in the this particularly in the least square adjustment is very important. So outlier detection is a very important job that you can do. As I said, any observation which is more than 3 sigma by rule are outlier. So you can say they're blunder, something's going on. So this is, I put it because I found it important to know. An experienced surveyor who returned to USQ to finish his degree once commented that all research effort and computational time to mathematically detect blunders seems a little bit complex. Why not just put more effort into field checks, guys, to stop blunders before they get into the analysis stage? So prevention. Always check your field work before you go trouble trying to identify them and do lots of work. So move on. Another element which is important in many statistical tests, as well as least square adjustment in particular, is error ellipse. Error ellipse is a very good tool to display and describe the uncertainty in two-dimensional. For example, easing and northing, like angles and bearing and distance. So error ellipse drew from standard deviation of confidence interval or confidence level around 40%, and if, as we know, if we want to have 95% confidence interval, the K factor for ellipse is 2.5 this time, not 2, or 1.96 in one-dimensional thing. So you can see we always have semi-minor and semi-major axis. In this case is bearing and distance. So it shows in easing and northing basically. So another definition that we need to know for error analysis is circular confidence region. So nowadays, or in recently, the new descriptive representation of two-dimensional uncertainty rather than error ellipse, especially in GNSS and GIS standard thing, they start to say circular confidence region. What you need to know is it's good to have circular or CCR, circular confidence region, to represent two-dimensional uncertainty, but still in surveying we prefer error ellipse or we basically write than circular region. But I put it because it's very common in GNSS and you might see it around in one of the, our specifications, so it's good to know what does it mean or how it's gonna be calculated. So circular confidence region can be derived from error ellipse. So if you have an error ellipse, you can simply get the, using the formula we have here, you know, A and B, which is a semi-minor and major basically axis of the error ellipse. So we have A and B. Yep. So you can put them here. You can basically calculate the radius of the circular region. But can we do the other way around? If I have the radius of circular region, can I get A and B? No. The answer is no. It's the one-way equation. So don't try to do the other way around. So, and look at the example here, and you can see how the CCR becomes less representative as the ellipse elongates. So if you have the, as you can see, if we have the accuracy between two-dimensional is pretty much equal. For example, say accuracy of distance and angle measurement are quite similar. So you can see the circular region is very close to error ellipse. But as one has better accuracy than the other one, and error ellipse elongate, then you can see the circular region is getting less representative of the error ellipse. So Experienced surveyor apply relative and absolute criteria to surveys every day, even if they're not conscious about that. They're doing like intentionally or unconsciously, and it's pretty much a standard type thing in construction, mining, surveying, any other type of survey job like cadastral, and they're all critical. In the first section, we try to talk about the terms of relative and absolute uncertainty. We talked about the error ellipse, which they are playing the important role in relative uncertainty between the points, and also say two-dimensional representative of uncertainty. So it's a graphical representation, and it can help us to identify the basically plan a project prior to the fieldwork, identify any error, and make sure that we can use the correct instrument and correct procedure to achieve the certain accuracy that is required. So, talking about the relative and absolute. So relative is between 2 points, absolute is regarding to 1 point only. Let's have a look at the example. Just imagine we have a small survey project for a trucking company. We have a long narrow lot. We want to set out the garage, we're going to set out the office, we're going to set out the water supply and electrical supply lines. We have the roughly dimension of the lot. We have the instrument specification. As you can see, is 12 millimeter plus 5 ppm. And the precision plus for the angular is plus or minus 3 seconds. If you look at the study book, you will see the angle precision is plus or minus 2 seconds, but also we have an error in pointing, which is 1 mil. Then the overall angular accuracy is going to be plus or minus 3 seconds. This is got served from study book examples. You can find obviously more detail over there if you like, or in future, but I will go to about this example to show you how it's going to work. So what we want to do, we want to analyze the accuracy of the setting out those corner of the basically buildings, as well as those water supply and electrical supply lines, and we see whether we can achieve it. So using the generic observation line to estimate uncertainty, we can, as this exercise is a form of pre-analysis, so we don't have measurement, we just guesstimate, or we do the pre-analysis for the measurement. It's basically, you can simply use the spreadsheet if you like, but if I assume generic south line is approximately 350 meter at 160 degree, so the bearing and distance for that garage or south line, and for the north or east line, sorry, that one was south, this one is east. If I say it's approximately 30 to 60 meter at 115 degrees. So if each certain point, so if you put those numbers in the formula of error propagation, you can get the or S or sigma, whatever you want to call, for delta northing and easting, and then you can get the relative. So if I want to get the relative uncertainty for each of these lines, for example for this line, which is north-south for the garage, so north-south, it can be relative uncertainty for line north-south can be, because it's going to be 8 square plus 8 square, which is 11 millimeter. Same thing can be for east-west. For east-west, I can say it's going to be 10 squared, 10 squared, which is line of east-west. It's going to be 14 millimeter, which is basically what is written here. Same thing for the office. You can put these numbers in and get this. They're very close to each other, 2 and 3, gonna give you the same answer. So if it's like, for example, squared 4 plus squared 2, sorry, 2, it's gonna be 4 plus 4, 8 squared, it's gonna give you 4 mil. roughly, plus or minus 4 for line north south of office. How about east west? East west gonna be 4 squared plus 4 squared, which is gonna be roughly plus or minus 6 millimeter, so which is here. And then you can say front and back of the service. You can do the same thing, get the relative uncertainties for each of those lines. So you can have the position, like absolute uncertainty for each of those points using the formula of error propagation, and then you can have relative uncertainty for each of these lines. So in conclusion, I can give you some hints. Always use the arbitrary coordinate system for error analysis. Don't bother to go through the exact number because it's pretty much giving you the same answer. Use a spreadsheet. It's very useful tool for analysis. Always use the software in error analysis and adjustment and planning. For example, for least square adjustment, it's going to be StarNet. We're going to have a tutorial on StarNet. I'm going to show you how you can do that. But it's also crucial for you to know and understand the error analysis and the statistical surveying. You can't really ignore it, because if you don't understand the error sources and error magnitude, no matter how good you are working, if you can't meet the standard requirement for your job, it's not just worth it. So it's very important for us to understand these concepts. So in conclusion, I can say we try to develop a model for surveying tasks to identify the components of uncertainty and nature of the uncertainty. We try to find our linear and nonlinear models, how we're going to calculate the error propagation. We know how we can get the sigma, whether we're from type A or B, which is whether we can calculate it ourselves or from experiences, or we can use the manufacturer specification. We can decide on the computation method to evaluate the uncertainty of the random, or using the propagation of the random error least square adjustment. Basically, we've learned that we can't really on the test solely. So we've learned about the uncertainty budget. And we've learned about that if we want to have the better confidence interval, like 95%, we have to consider the coverage factor, or K, and times to sigma gives you a different confidence interval. We've learned about the basically how we're going to analyze the results and decide which method we're going to use, with how many, for example, how many times we want to measure the angle to meet the requirement or specification. So tests are good, but you can't really rely on them. If you fail to meet, you have to revisit error component and try to find how you can improve your precision, whether it's repeating the measurement can improve your precision, whether it's like using the better equipment. Yeah, all sorts of decisions can be made. So I hope you enjoyed this lecture. This is a nice code. I leave it for you to read and understand it. Thank you for